You're tuning into the deep dive, and you're here because, well, you're like us, fascinated by how things work.
And keen to get the important stuff without getting totally lost in the weeds.
Exactly. Today, we're pulling apart something absolutely vital: aircraft fuel systems. We've got this really detailed chapter, and honestly, it's amazing how much engineering goes into just keeping planes powered up safely.
That's right. If you've ever looked up at a plane and just wondered, how did that fuel get from the tank all the way to the engine? Well, this deep dive is definitely for you.
We're going to explore the basic needs these systems meet, the science behind the different fuels.
Which is surprisingly complex.
Right, and how the designs change for different planes, the components involved, and crucially, why maintenance is just so critical.
Yeah, get ready for some, I think, some genuine aha moments about a world most people don't really think twice about.
Okay, so starting right at the beginning. Every powered aircraft needs fuel. Seems obvious.
Pretty fundamental, yeah.
But what really jumps out is the sheer level of oversight. These aren't just, cobbled together. They're governed by incredibly strict FAA regulations. We're talking Title 14 of the Code of Federal Regulations.
Absolutely. And these aren't just suggestions. They are hard rules for how these systems have to be designed, how they get certified. Safety is paramount.
And one of the biggest demands, it seems, is uninterrupted fuel flow. Clean fuel flow.
Exactly. No matter what the aircraft is doing, sharp turns, climbing, descending now, that fuel has got to keep feeding the engine without any interruption.
That sounds like a massive engineering puzzle right there.
It really is. Think about the physics involved. And the fuel itself has to be clean, contaminant-free. Any little bit of dirt or water could cause huge problems.
And it's not just the flow. The actual airframe has to be strong enough to cope with all that fuel weight shifting around during maneuvers.
Right, the structural integrity is key. What's interesting is how these requirements pop up across the regulations. You've got Part 23 for small planes, Part 25 for the big transport jets.
Part 27 and 29 for helicopters.
And even Part 33, which deals specifically with the engines and how they interact with the fuel system. It's all interconnected.
A whole ecosystem of rules, basically. And there's some really specific ones, like a single fuel pump can't draw from more than one tank at the same time. Why is that so important?
That boils down to reliability and predictability.
Okay.
If one pump could drain multiple tanks, you could accidentally empty one tank completely.
And suck air into the lines.
Precisely, which could starve the engine. So this rule ensures a stable, known fuel supply. Always. No nasty surprises.
Makes total sense. Now, turbine engines, jets, they have some different needs, right? Something about venting, and they can handle a bit of water.
Correct. Turbine fuel systems have their own venting standards. And yeah, some of those actually fall under EPA rules too, Part 34.
EPA. Interesting.
But the water tolerance is quite something. The regulations actually specify tests where the fuel has a fair bit of water dissolved in it, even some free water.
Free water, like floating around.
Sort of, yeah. Saturated fuel plus a bit extra. And the system still has to work even after that fuel gets cold enough for ice to potentially form.
Wow. That's a world away from how you'd think about gasoline engines.
Definitely different challenges. And that brings us to another key idea: fuel system independence.
Making sure one problem doesn't cause a total failure.
Exactly. It's built-in redundancy. If, say, a pump fails or a line gets blocked, it shouldn't automatically mean the engine quits. You need backup pathways.
A single point of failure is a no-go.
Absolutely not.
Something else that caught my eye was lightning protection. You don't immediately think lightning and fuel system together.
But you have to. The system needs to be designed so a lightning strike, whether it's a direct hit or one of those glancing blows called swept strokes.
Right, often on the wings.
Or even these electrical effects called corona and streamering near fuel vents. None of that can ignite the fuel vapors.
Corona and streamering, like static discharge.
Kind of. Corona is a visible electrical discharge, like a little glow. Streamering is more like those feelers of electricity you see just before a lightning bolt connects. The system has to prevent any spark near the fuel.
Makes sense. So stopping any potential ignition source near flammable stuff?
That's the core job. And beyond emergencies, the system just has to deliver the right amount of clean fuel to the engines and the APU, the auxiliary power unit.
Under all conditions.
All conditions. Plus, the pilots need a clear, accurate reading of usable fuel, and they need confidence in that supply, even when the fuel's sloshing around.
And there needs to be a way to safely drain fuel for maintenance,
Right.
Or isolate sections.
Yes, safe removal and isolation are required. And the system needs to be designed to contain fuel as much as possible during a survivable crash landing, minimizing fire hazards. They even consider things like landing gear failures on certain planes.
The level of detail is incredible. What about the tanks themselves? They're not just simple boxes.
Oh, far from it. They have to be incredibly strong, withstand flight loads, be isolated from people, protected from temperature extremes.
And hold enough fuel for a safety margin, right? Like 30 minutes of flight at full power.
At maximum continuous power, yes. That's a key airworthiness standard.
And for the big jets, there's fuel jettisoning or dumping. We saw diagrams for that. Why do they need to do that?
Primarily for situations where a large aircraft takes off heavy, maybe near its maximum takeoff weight, and then has an issue requiring an immediate return to land.
Ah, so they'd be too heavy to land safely.
Potentially, yes. Landing weights are usually lower than takeoff weights. Jettisoning allows them to quickly dump fuel safely away from the aircraft, usually from the wingtips to get down to a safe landing weight. Boost pumps push the fuel to dump chutes or nozzles.
A rapid weight loss plan for emergencies. And the tanks also need to avoid just spilling fuel out the vents during normal flight.
Correct. Vent systems are designed to prevent significant fuel loss during maneuvers or even during fuel transfer between tanks.
And finally, the refueling systems themselves have rules to prevent mistakes.
Absolutely. Preventing putting in the wrong fuel type, avoiding contamination during fueling, and ensuring the whole process is safe for the ground crew in the aircraft.
Okay, that covers the why and the what's the system rules.
Right.
Let's talk about the actual fuel. The chapter is crystal clear. Use only the manufacturer-specified fuel. No mixing allowed. Ever.
That is rule number 1, non-negotiable. And basically you have two families, AVGAS, aviation gasoline, for reciprocating piston engines.
Like in smaller propeller planes.
Exactly. And then turbine engine fuel, or jet fuel, which is essentially kerosene, for jet engines and turboprops.
Let's tackle AVGAS first. It's a special hydrocarbon blend from crude oil. Key features.
High volatility is a big one. It evaporates very easily, and it's highly flammable, low flash point. That's quite different from jet fuel.
And that volatility is important for the engine.
Crucial. In a piston engine with a carburetor, the liquid AVGAS needs to vaporize easily to mix properly with air for combustion.
But too much or too little volatility causes problems.
It's a balance.
Too
little, and you get hard starting, slow warm-up, maybe poor acceleration, too much, and you risk things like vapor lock, uneven fuel distribution to cylinders, or even oil dilution in some engines.
The source also talks about detonation. Sounds bad.
Very bad. Detonation is like a small, uncontrolled explosion inside the cylinder. It happens when the fuel-air mix ignites violently due to excessive pressure or temperature before the spark plug is supposed to ignite it smoothly.
Instead of a controlled push, it's a damaging shockwave.
Exactly.
Yeah.
It hammers the piston, the cylinder head, valves, can lead to serious engine damage.
So AVGAS is specifically made to resist this.
Yes, it's refined to have a high resistance to detonation based on its ignition characteristics and burn speed.
What are the warning signs? Pinging, knocking.
You might hear that, although it can be tough to pick out over engine noise in a plane. A much more reliable indicator is a rise in cylinder head temperature. That's a key thing pilots monitor.
And the pauses. What triggers detonation?
Using the wrong fuel grade is a big one. But also letting the engine overheat, running it too lean for too long, pre-ignition, where something hot in the cylinder ignites the fuel early, or even high RPM with low airspeed can contribute.
So maintenance is key here. Checking plugs, valves.
Absolutely. Ensuring the engine is healthy and operated correctly and using the right fuel are the best defenses.
Okay, and we measured this detonation resistance using octane ratings and performance numbers.
That's right. Octane rating measures how much compression the fuel can handle before detonating. It's compared to reference fuels made of isooctane and heptane. 100 octane means it performs like pure isooctane.
And those double numbers like 8087 or 100-130.
But the first number is the octane rating under lean mixture conditions, typical for cruising. The second number is the performance number under rich mixture conditions, like during takeoff or high-power climbs. So it describes performance across the operating range.
Tetraethyl lead, TEL. That used to be common.
Still is, in some grades like 100LL. TEL is very effective at boosting the octane rating, resisting detonation. It also provides some valve lubrication as a side benefit. But you need other additives too, like scavengers, to prevent lead deposits building up.
And 100LL means low lead, but it's not lead-free.
Correct. It has significantly less lead than the old 100-130 grade, but still more than, say, 80-87. The goal was a single fuel for most piston engines, but using 100 LL in engines designed for lower octane fuel can sometimes cause issues like spark plug fouling.
And there's a push for unleaded AVGAS for environmental reasons.
A big push. Developing a high-performance, reliable, unleaded alternative that works across the existing fleet is a major ongoing effort in the industry.
So how do you make sure the right AVGAS goes in the right plane? Mistakes sound catastrophic.
They can be. So identification is critical. You have color coding. The fuel itself is dyed specific colors, plus labels on tanks, trucks, hoses, and the filler port on the aircraft.
Visual checks.
Yes, and there's a physical check, too. The nozzle for dispensing jet fuel is wider than the filler neck for AVGAS tanks. It simply won't fit.
A good safeguard. What about keeping AVGAS clean? Contamination.
Filters are used during transfer and storage, and aircraft tanks have sumps, low points where water and heavier particles collect. Draining these sumps before flight is a critical check.
And water is the main enemy.
It's the most common contaminant, yes. It doesn't mix well with AVGAS and settles out.
How does it even get in there?
Mostly condensation. Temperature changes make the air inside the tank breathe, pulling in moist air. As it cools, water condenses out.
So keeping tanks full helps. Less airspace.
Exactly. Filling up after flight is a good practice. Too much water can obviously cause the engine to sputter or quit if it gets drawn into the carburetor.
And even dissolved water can be a problem at altitude? Freezing.
Yes. As the fuel gets colder, climbing up, dissolved water can come out of solution and form ice crystals. These can clog fuel filters. That's a serious risk.
And that's why additives like Prist come in. Anti-icing.
Correct. Additives can lower the freezing point of the water or prevent ice crystals from sticking together and blocking things.
Okay, that covers AVGAS pretty well. Let's switch gears to turbine fuel, jet fuel. How's it different?
Fundamentally different stuff. It's more like kerosene. It's less volatile, higher flash point, higher viscosity, meaning it's thicker than gasoline. Its molecular structure is different, heavier hydrocarbons.
Designed for continuous burning in a jet engine, not the intermittent explosions of a piston engine.
Exactly. And it often has additives for corrosion prevention, oxidation stability at high temps, anti-icing, and importantly, preventing microbial growth.
Microbial growth in fuel.
Yes, that's a much bigger issue with jet fuel than AVGAS. We'll get to that.
Okay. What about volatility in jet fuel? Is it still a factor?
It is, but the trade-offs are different. Lower volatility is generally good, reduces evaporation loss, less risk of vapor loss, but too low can make cold weather starting harder.
So different types exist, like Jet A versus Jet B?
Right. Jet A is the standard in the U.S. Jet A1 is similar, but has a lower freezing point, making it more common internationally. Jet B is a wider cut fuel, includes some gasoline fractions, making it much more volatile and suitable for extremely cold climates like northern Canada and Alaska. It is a much lower freezing point, but also a lower flash point.
And purity is still key, but the contaminants are different threats.
Solid particles and icing are still concerns, yes. But water and microbial growth are the really unique challenges for jet fuel.
Why is water such a bigger deal?
Jet fuel can hold more water in a dissolved state than AVGAS. It's just chemically more accommodating to water. And because of that,
microbes have a place to live.
Exactly. Bugs, bacteria, fungi, they love the interface between fuel and any free water that settles out in tanks. They form this slimy layer, a biofilm.
And that causes problems.
Big problems. It can clog filters, corrode tank linings, even degrade the fuel quality itself. It's a constant battle.
How do you fight it? Biocides.
Biocides are chemicals added to kill the microbes. Good housekeeping is also vital. Regularly draining water sumps from storage tanks and aircraft tanks, minimizing water entry. Some anti-icing additives also help inhibit microbial growth.
So, best practices. Keep water out, drain sumps, maybe use biocides.
That's the approach. And always be vigilant about icing, especially at altitude. Follow the manufacturer's procedures.
Okay, fuel's covered. Now, the systems themselves. The chapter says designs vary, but the basic jobs are the same.
Right. Store it safely, deliver it cleanly, at the right pressure and flow under all conditions. That's the mission, whether it's a Cessna 172 or a Boeing 787.
Let's start small. Single-engine planes. High wing versus low wing makes a difference.
Big difference, mainly in how the fuel gets to the engine. High-wing designs often use gravity feed.
Like the diagram in figure 1412, tanks are above the engine, so gravity does the work.
Pretty much. Very simple. You need vents, a shutoff valve, maybe a selector valve if there are multiple tanks, and a strainer. But no pumps required for normal operation.
Elegant simplicity. But low-wing planes, tanks are below the engine. Need pumps then, like figure 1413 shows.
Absolutely. You need pumps to lift the fuel. Typically, you'll have an engine-driven pump as the main one and an electric auxiliary pump.
What's the electric pump for? Backup.
Backup, yes. Also crucial for starting, priming, and preventing vapor lock, especially at high altitude where the lower pressure makes fuel boil more easily in the lines.
And the selector valve usually only lets you pick one tank at a time.
Generally, yes.
Yeah.
Again, to prevent sucking air if one tank runs dry unexpectedly.
Makes sense. Now, some high-wing planes, especially with fuel injection, use a mix, gravity plus pumps, like the Teledyne Continental system shown.
Yeah, those systems are a bit more complex.
Yeah.
Fuel injection needs consistent pressure, free of air bubbles. So gravity might feed fuel to a reservoir or accumulator tank.
Okay.
Then an engine-driven pump draws from that reservoir, pressurizes the fuel, and meters it based on engine speed. There's usually still an electric pump for starting and backup.
And it sounds like there's a system to return any separated air back to the tank.
Yes. Often the selector valve arrangement helps divert separated air or vapor back to the selected tank's vent space. The pressurized fuel goes to a fuel control unit, which fine-tunes the flow based on throttle and mixture settings, then out to the injectors.
More intricate. Now, scaling up, small multi-engine planes. More complex again, I assume.
Naturally. 2 engines, often more tanks, cross-feed capability becomes important. Let's look at a typical low-wing twin, like in figure 1416.
Okay, main tanks, maybe auxiliary tanks, boost pumps mentioned here.
Yes, often electric boost pumps in the main tanks. They pressurize the whole system, help prevent vapor lock, and can sometimes run the engine if the engine-driven pump fails. Also used for priming and starting.
And selector valves for each engine, allowing cross-feed.
Correct. Each engine has a selector. You can usually feed an engine from its own main tank or the opposite main tank that's cross-feed, useful for balancing fuel load. O-tanks usually only feed the engine on the same side, though.
So from the selector through a strainer to the engine-driven pump.
Which often has a vapor separator, sends vapor back to the tank, and then supplies the fuel control unit for that engine.
Which meters fuel to the injectors. Got it. Lots of redundancy. What about a high-wing twin? Still use gravity?
Sometimes partially, yes, combined with electric pumps. Figure 1417 shows a system where electric pumps draw from the selected tanks and feed the fuel injection system directly. Still needs selectors and strainers, of course.
Okay. And briefly, those large, older reciprocating engine planes, like the DC-3 example, still flying.
Many are, often carbureted. The DC-3 system described is fairly typical. Selector valves, engine-driven pumps, strainers, cross-feed capability. Older ones might have had a manual wobble pump for priming.
A wobble pump.
Yeah, hand-operated pump. Later models used electric pumps. But the basic principles are similar, getting fuel from tanks to the engines reliably. Always needed a specific manual for those older birds, though.
Absolutely. Now, the big leagues. Jet transport fuel systems, described as a collection of subsystems.
Yeah, that's a good way to think of it. Storage, vent, distribution, feed, indicating. They all work together. And while details differ, the overall architecture is pretty similar across most large jets.
Integral tanks are standard, using the wing structure itself.
Yes, the wing box is sealed to hold fuel. Often a center wing tank or fuselage tanks too. These things carry enormous amounts of fuel. Think tens of thousands of pounds.
And optional fuselage tanks for long range add complexity.
Definitely affects fuel management.
Yeah.
You also have surge tanks, usually outboard in the wings.
What are they for? Overflow.
Overflow, yes. During fueling or due to thermal expansion, they're normally empty. They also connect to the vent system. Fuel can flow back into the main tanks from the surge tanks via check valves.
And venting is complex in these big planes, not just a simple pipe.
Oh no, it's a whole network connecting all tanks, usually venting through the surge tanks or overboard. It needs to work in all flight attitudes. Lots of check valves, float valves, multiple vent outlets are common.
Okay, then the distribution subsystem. Fueling, defueling, transfer, jettison.
Right. Fueling is almost always single-point pressure refueling. A nozzle locks onto a fueling station under the wing. Much faster and safer than over the wing for large volumes.
Automatic shutoffs.
Usually, yes. Controlled by level sensors in the tanks. Defueling often uses the same connection, using boost pumps or the fuel truck's pump.
And fuel transfer, moving fuel between tanks in flight.
Yes, using boost pumps and dedicated plumbing and valves. Important for managing the aircraft's center of gravity as fuel burns off. Some planes rely more on cross-feed running engines from different tanks rather than active transfer.
Like the DC-10 example diagram showing transfer pumps.
Exactly. That system uses dedicated pumps for transfer and jettison.
And the fuel feed system is the final step to the engines.
The core job, yeah. In-tank boost pumps, usually at least 2 per main tank for redundancy, push fuel through shut-off valves to each engine. Manifolds and cross-feed valves typically allow any tank to feed any engine.
Can the engines run without the boost pumps?
Jet engines generally can, yes. Their own high-pressure pumps can suction feed, but it's not the normal or preferred mode. Boost pumps ensure positive pressure.
And fuel heating is common to prevent icing.
Very common. Usually using heat exchangers with hot engine bleed air or hot engine oil, like that fuel-cooled oil cooler shown, keeps the fuel flowing freely at cold, high altitudes.
And the indicating systems are more sophisticated too, beyond just quantity.
Definitely. Fuel flow gauges per engine are primary instruments. Fuel temperature gauges, filter bypass warnings, low fuel pressure warnings for the boost pumps.
And quantity gauges are often capacitance type, no moving floats.
Right. They measure the electrical capacitance of probes in the tank, which changes based on how much fuel versus air is covering the probe. Very reliable, no moving parts inside the tank.
Let's quickly touch on helicopters, similar principles.
Fundamentally, yes, though designs vary hugely. Simple ones might be gravity feed, like the Robinson example.
Others, like light turbines, have boost pumps, filters, shut-off valves.
Correct. Maybe 2 boost pumps per tank, for redundancy, feeding the engine pump through filters. Pressure gauges, filter clog indicators, quantity probes are typical.
And big transport helicopters, complex systems like jets.
Pretty much. Multiple tanks, cross-feed, pressure refueling, similar concepts to large fixed-wing aircraft, always need the manual for the specific type.
Okay, great overview of the systems. Let's dig into the components themselves now. Fuel tanks, we mentioned 3 types.
Rigid removable, bladder, and integral. The choice depends on the aircraft. All need to be non-corrosive, vented, and have a sump with a drain for contaminants. Baffles inside reduce fuel sloshing.
Rigid removable tanks, metal or composite, bolted or strapped in.
Usually, yeah. Made of aluminum, steel, or composites. You can take them out for repair, which is handy. Welding repairs require extreme caution. Vapors must be purged completely first.
Bladder tanks, flexible bags inside a structure.
Exactly. Reinforced flexible material. Good, because you can often install them through smaller openings. They need to lie smooth inside, no wrinkles. Used in all sizes of aircraft. Repairable by patching. Need to be kept wet or oiled if stored dry.
And integral tanks, part of the plane's structure.
Right. Common in wings of larger aircraft. The structure itself is sealed to hold fuel. Access is through sealed panels. Entering them requires strict safety protocols. Empty tank, purged, respirator, spotter. Usually has sophisticated pump and valve systems inside.
Okay, tanks covered. Fuel lines and fittings. Rigid and flexible.
Both. Rigid lines are usually aluminum alloy, maybe stainless steel in high vibration or fire-prone areas. Flexible hoses have synthetic rubber liners, braid reinforcement, often fire sleeves in hot areas. Standard ANMS fittings connect them.
And proper support is important.
Clamps. Very. Rigid lines are clamped to the airframe at specific intervals using cushion clamps. Need a slight bend between supports for vibration and thermal expansion.
Fuel valves. Lots of different types and functions.
Tons. Simple selectors in light aircraft. Shut-off, transfer, cross-feed valves and larger ones can be manual, electric motor-driven, or solenoid-operated. Clear position indication is crucial.
Manual gate valves mentioned for fire shutoff.
Yes, common as firewall shutoff valves because they don't need power. Also used for isolating pumps or for defueling. A sliding gate blocks the flow.
Motor-operated valves for remote locations.
Common on large aircraft, usually electric motors driving gate or plug valves, often have manual overrides.
And solenoid valves for quick action?
Yes, electromagnets open or close a poppet. Very fast acting.
Okay, pumps. We mentioned engine-driven and auxiliary boost pumps. Any other types?
Well, you have hand pumps, like the old wobble pumps or simple primer pumps for starting.
Still see primer pumps.
Sometimes, but electric boost pumps often handle priming now. Less fire risk than fuel lines in the cockpit. Centrifugal boost pumps are very common. Auxiliary pumps, often electric, sometimes submerged in the tank.
Ejector pumps, what do they do?
They use the Venturi effect, using a stream of moving fuel to create suction to help scavenge fuel from corners of the tank, or ensure the main pump inlet is always flooded with fuel. No moving parts, rely on flow from another pump.
Pulsating electric pumps in general aviation.
Yes, often solenoid-operated piston pumps. Used for starting, backup, anti-vapor lock. They cycle on and off.
And the main engine-driven pumps are usually vane type.
Typically positive displacement vane pumps. They have relief valves to prevent overpressure. Some are pressure compensated, adjusting output based on engine needs.
Filters and strainers. Critical for cleanliness. Strainers for big stuff, filters for fine stuff.
Generally, yes. Strainers are coarser mesh. Filters are finer, often rated in microns. Turbine engines need micronic filtration, down to 10-25 microns because their fuel controls have very tight tolerances.
Where are filters located? Tank outlets? Main strainer?
Usually a screen at the tank outlet or a boost pump inlet, then a main strainer or filter, often with a drainable bowl like a gascolator on light planes, located between the tank and the engine's metering device. Turbine systems have very fine filters right before the fuel control unit, often with bypass capability and clog indicators.
Fuel heaters, again, air-to-fuel or oil-to-fuel heat exchangers.
Those are the main types, yes. To prevent fuel icing, especially in jet fuel at altitude, can be manually controlled or automatic with thermostats.
Indicators. We covered quantity, flow, temperature, pressure. What about warnings?
Low-pressure warning lights are standard, usually triggered by pressure switches at pump outlets, filter bypass lights, and valve position indicators.
Valve and transit lights showing when a valve is moving.
Exactly. On complex systems with motorized valves, lights indicate when a valve is between fully open and fully closed. They go out when it reaches the selected position. Or annunciators might show open or closed. Digital displays often show valve positions graphically.
Okay, that's a lot of components. Let's shift to maintenance and troubleshooting. Always follow the manual, right?
Rule number 1, always. You need the manufacturer's data, specialized training, and the right tools. Troubleshooting requires understanding the system flow and using logic, often aided by the manual's charts.
Finding leaks sounds like a common task. Visual inspection, stains, odors.
Yes. Close inspection is key. Leaks often happen at connections or seals. AVGAS might leave a dye stain or clean patch. Jet fuel is oilier, tends to collect dirt over time. Any leak where vapors can collect is a serious hazard and must be fixed before flight.
And there's a leak classification system. Stain, seep, heavy seep, running leak.
Yes, help standardize reporting and deciding on action based on the leak rate or size.
Repairing leaks often means replacing gaskets and seals.
Very often. Use the correct new part, check shelf life, clean surfaces meticulously, follow torque specs and sealant procedures.
Tank repairs depend on the tank type.
Absolutely. Riveting, welding, soldering for rigid tanks, always after purging vapors. Sloshing compound for minor seepage sometimes. Bladder tanks are patched with specific kits. Integral tanks are the most complex, often requiring sealant removal and reapplication following very precise procedures. Corrosion is always something to look for during tank repair.
Fire safety is paramount throughout all this. Fuel, air, ignition source.
Keep them separate. Control ignition sources, especially static electricity from fuel flow or even clothing. AVGAS is highly volatile. Jet fuel less so, but still very dangerous, especially as mist or near hot surfaces. Empty tanks or bombs waiting for a spark. Purge them properly. Have the right fire extinguisher, Class B CO2 or dry chemical ready and know how to use it. Use bonding wires during fueling defueling.
Contamination checks. An everyday thing.
Should be. Daily sump draining, periodic filter checks. Turbine engines are especially sensitive. Something jet fuel isn't foolproof due to its viscosity. Filters are critical.
Main contaminants: water, solids, surfactants, microbes, wrong fuel.
Those are the big ones. Water comes from condensation mostly, settles low. Drain it daily. Solids get trapped by filters. Prevent entry by keeping things clean and capped.
Surfactants, what are they?
Basically soaps or detergents, natural or from handling. They mess up water separation, keep dirt suspended, and can gum up filters. Harder to spot, but slow water settling is a clue.
Microbes, the jet fuel problem, need water to grow.
Yes, they live at the fuel-water interface. Form slime, clog filters, cause corrosion. Minimizing water is the best defense, plus biocides if needed.
And wrong fuel contamination is catastrophic.
Potentially fatal. Double, triple check you're using the right fuel. Markings are clear for a reason. If in doubt, ground the aircraft and drain it.
How do you detect these? Visual check for bright and clear fuel? Test kits.
Visual check first. Cloudy or hazy needs investigation. Test kits exist for water content, microbial activity levels, specific bacteria fungi types. Labs can do full analysis if needed.
Fuel contamination control is everyone's job, from refinery to aircraft.
It's a chain of custody. Suppliers filter and test. Ground handlers need procedures. Technicians need to maintain filters, drain sumps, inspect samples. Never take clean fuel for granted.
Okay, last big topic. Fueling and defueling procedures. Technicians often do this.
Very often. And procedures vary. Fueling sequence can even affect structural loads on some large aircraft. Always check the manual if unsure.
Fueling always outside. 2 types. Over the wing and pressure refueling.
Correct. Never in a hangar. Over the wing is like a car. Pressure refueling uses a single-point connection, much faster for large volumes.
Key precautions for both. Correct fuel type is number one.
Absolute critical. Check placards. Use bonding wires before opening caps to prevent static sparks. Keep nozzles clean. Handle hoses carefully.
Pressure refueling needs the right pressure, understanding the control panel.
Yes. Connect the nozzle correctly. Operate the panel valves as required. Follow the sequences specified.
Safety with fuel trucks. Positioning, bonding.
Position for easy exit. Set brakes. Chock wheels. Bond truck to aircraft before fueling. Walk only on designated wing areas. Treat nozzles carefully. Double-check caps are secure afterwards.
Defueling, same safety rules apply. Bonding outside, fire extinguishers.
All the same precautions.
Yeah.
Might be needed for maintenance or removing contaminated fuel. Again, sequence can matter. Pressure-fueled planes usually defuel via the fueling port. Over the wing, often via sump drains.
What happens to defueled fuel?
Depends. Contaminated fuel must be segregated and disposed of properly. Good fuel might be reusable according to manufacturer instructions, but handle it carefully. Keep it clean. Don't mix types.
And fire hazards during defueling are always present.
Static, vapors.
Constant risk. Work outside, wear appropriate clothing, cotton better than synthetics.
Right.
Control all ignition sources, no smoking, limit electronics. Bond everything. Clean up spills immediately, wipe small ones, flood large ones with water. Have extinguishers ready and know how to use them. Position trucks for quick escape. Wow. Okay, that brings us to the end of this incredibly detailed deep dive into aircraft fuel systems.
Yeah, we covered a lot of ground.
We really did. From the basic needs, the different designs, the fuels themselves, AVGAS, jet fuel, all their quirks.
The components, tanks, lines, pumps, filters, heaters, indicators.
And the absolutely critical maintenance, safety checks, fueling procedures. It's a huge topic.
It really is remarkable. You know, what seems like just filling up a plane involves this incredibly complex, highly regulated system, all built around safety and reliability.
Totally. So maybe the next time you see an aircraft, on the ramp or flying overhead, take a second to think about that intricate web of pipes, pumps, tanks, and sensors.
All working together to deliver that vital lifeblood to the engines.
Exactly. All based on the principles we talked about today. It kind of makes you wonder, doesn't it? What other things that seem simple on the surface have this kind of hidden depth and complexity?
That's a great thought. Maybe listeners could even look up the fuel system for a specific plane they're interested in, or the fueling regulations at their local airport.
Yeah, absolutely. Well, thanks for joining us on this deep dive.
My pleasure. It was fascinating to explore.